Good afternoon, this is Schweitzer, and we're going to do a little quiz, little video here on intermolecular forces. Now, this is an absolutely huge topic, absolutely huge topic, and I don't know that I couldn't make 10 videos on this particular topic. So this is an overview of it. We did all this stuff in honors chemistry. I'm just trying to reiterate some of this stuff and break some rust off. But ultimately, it's up to you to make sure you have full functioning of the different types of intermolecular forces and how they work. And you have a path in your brain that you can walk down to dissect certain things involving intermolecular forces. So what is an intermolecular force? Okay, two neutral substances attract above. For what reason is this attraction? Identify the force. Add charges to the picture to show the scenario. Okay, so why would two things that are neutral attract? We know if one's positive, one's negative, that they attract, but the only thing, like an ionic compound, but in this situation, where it's neutral and they attract, you have to have some sort of positive charge. And in this case, because they're neutral, it's not a big charge. So we call this, looks like this, little S-looking thing. It looks like a bigger version, might look like, would look something like this, partial. So it's the Greek symbol delta. This is the lowercase version, uppercase version, mean difference, small difference. Let's say positive, and this side must be negative. If you have attraction, you have opposite charges. And then we get attraction here. We never show a full dash here, by the way. That would be a covalent compound. It's not a sharing of electrons. It's a weak intermolecular attraction. The nucleuses cannot move. Let's just say we have a nucleus here. Okay. They can't move. The positives are stuck in the positives, but we can't have electrons moving. This side's positive, so for one reason or another, more negatives are over here than over here. So we have more negatives here than over here, and therefore they attract. There's a lot of ways this can happen, but ultimately this is it. Okay, two neutral substances attract. Okay, to that, a full charge of -1. Okay, a full charge gained equals -1. The only bond type where this occurs would be what? If you actually have a -1 charge, it would be ionic. Okay, a smaller charge is called a partial charge, and is symbolized with this little guy here. Okay, negative or positive. All right. All right. There's that. I kind of just drew that all out. There we go. All right. Each group is comprised of two neutral substances, positive equal negative. Redraw the pictures showing each attraction. All right, ionic. Now we do ionic here. We'd actually, I'm gonna abbreviate this somewhat because I don't want to take a ton of time just drawing all these negatives. But essentially, we'd have to have one of these negatives jump over this guy, okay? And you have to have more negatives on this side than on this side. I'm going to exaggerate that a little here. This side becoming -1, this guy becoming +1, and this would be ionic, and it is a form of being like the most polar thing you can get. Right? All right, so here, London dispersion forces. What happens here? Okay, just in this case, once again, this guy here has two positives, okay, and for whatever reason, because of movement of electrons, one side becomes somewhat negative, okay, and the reason why is because it's random movement electrons, and this side therefore becomes positive. All right, and these negatives push away the electrons on the other side. We call that an induced charge. This guy happens to have a little bit of a negative charge here because of random movement electrons. Comes close to this guy and shoves them away, and all of a sudden now this is partial positive, and this is partial negative, and you get attraction. We call that London dispersion forces. Is this a polar molecule? No. There's no transfer of an electron. All right. It's a non-polar molecule. Right? This is a temporary thing. It goes away, it comes back. Okay. All right, and you don't necessarily need to be a transfer an electron to be polar. By the way, we'll see that happen here. So hydrogen bonding. Okay, now a little bit different situation here. One of the atoms, for whatever reason, is highly electronegative, and it is going to, let's say this guy right here is the highly electronegative atom. It draws more electrons toward itself than this one. And we start to get a situation where this side becomes partially negative, this side becomes partially positive. This is a permanent situation. This guy always has that highly electronegativeness. So this atom here could be a nitrogen, could be an oxygen, could be a fluorine. These are the big ones, but everything has some amount of electronegativity. Therefore, this side here could be the opposite. I'm going to call this, let's say this is X, and let's call this guy Y. Okay, so now X is here and Y is here. Well, now the electrons are also over here, so this guy's partial negative here, this guy's partial positive here, and you'll notice that, this is a nice attraction here, and it's permanent. Okay, this is a polar molecule. Okay, just general understanding of different types. This would be these guys. They're both the same. Okay, undispersion forces. Let's keep moving here. And okay, so this particular section is kind of like little walks through mazes. And you got to kind of have this in your brain to work through things. So we have a couple different situations here. So we know two particles have charges and they attract. Next obvious question might be, how do these particles acquire charge? Okay. So whether it's a partial charge or whether it's a negative charge, and it's going to go on various options here. So we could have, for example, here electron transfer. Electron transfer, okay, creates a ion, and it's called ionic. Okay. Electron imbalance. Electron transfer here, imbalance here. And this is something you just need to have a mental map. Mental map is a good word. Creates a partial positive, and a partial negative, and they attract. We have an electron imbalance. All right. Again, I'm using these things here. Okay. Creates a, because we have a partial imbalance, which means they're just shoved to one side, the other one, calls partial charges, partial positives and partial negatives, partial charges, which is called a, all right, either hydrogen bond or a dipole-dipole. So there's two options. You're just trying to continuously move along. A cation, anion would be right there. Okay, and this is ionic. So we could probably have an ionic down here. All right. So again, trying to just get the initial workings of this mental map. Ionic, London dispersion forces could be an option here. London dispersion forces, or this one could be something that would be like hydrogen bonding or dipole-dipole. All right, so there we go. What we got there. Okay, here we go. I did this a little differently. I did it in the middle here. Okay, so I did it a little differently. All right, same stuff. All right, so what are some characteristics of London dispersion forces? Okay, what factors cause dispersion force to be bigger? What term do we use to describe these characteristics? Which substance is not LDF? In which substance is LDF not present? Okay, so some characteristics of these guys. One thing I just want to make sure you know is this is a nonpolar substance. Nonpolar. Okay, it tends to be relatively weak. Okay, everything has it, even ionic. Every substance has. It may not be the number one strongest force, but so what causes things to be more amplified? Well, this is something you want to have in your brain right away. Check. If your mental pathway, pull this right out like the back of your hand, then you're on the right track. All right, so one, number of electrons, not mass. All right. The more, so this London dispersion forces is where we have electrons in an atom, and just because they can move, by some chance there are more electrons on one side than on the other side. And in 2 seconds later it could be flipped around. Electrons are very fluid. So the more electrons you have, the more likely this phenomenon happens. This phenomenon we use to describe is called polarizable. This is a big AP term. Anytime you see polarizable, you should be thinking London dispersion forces. And again, next one is number 2, would be long chains. Long chains, which is like your carbon compounds, can also be more susceptible to this, and therefore are more polarizable. If you have a long chain item, you say, why is London dispersion forces more prevalent in this thing? You say, the long chain causes it to be more polarizable. That's a good term to describe this moving electrons. Which substance is LDF not present? Well, it's present in all substances. That's kind of a bit of a trick question, okay? We'll have to check you on that. Okay, all substances have them. Some are just more. All right, so this is our little notes on this, okay? All right, so repeating kind of stuff we said. As they get longer, they get increased example of London dispersion forces, more polarizable. Okay, good here, polarizable. All right, so octane versus hexane. Okay, and if you looked at the melting points of these things, the melting points of these guys will start to go up for this one because it's got more attraction between the molecules. Okay. Good picture here as well, showing an induced dipole. This guy has an instantaneous dipole, and it causes another one to be produced next to it. All right, moving along. Again, properties of alkanes. This is looking at where we're not long chains now, but we have larger number of electrons. And look at the boiling points of these guys. It gets bigger and bigger and bigger as you go down. Okay, classic example, right, of London dispersion forces. Classic example of longer chains causing London dispersion forces. So again, look at the trend here. This is really for APs where they show a little data and then you need to answer that or justify that data with information that you know about bonding. Okay, sample example here. Okay, now again, you need to be looking at the data and then before even looking at the questions, you should be looking at this. Okay, what do I got here? All right, so I have all molecules here that are just carbons and hydrogens. So my brain here, what I do is like, okay, well, there's no highly electronegative atom. That might be one thing that I would think about. Okay, so and they're not all the same atoms. So I have a dipole moment. Okay, there is a dipole moment, and we'll talk more about that in a moment, I guess. Here, moment. But in this case, because it's not something where it's got a highly electronegative atom, that would mean that real strong forms of hydrogen bonding or dipole-dipole, those are kind of minimized. You know, these guys are going to be minimized to the point where it's not going to be a determining factor. What is the determining factor? We got a little longer chain, so if I look at this longer chain, I think, this could be a London dispersion force problem. And that's really what you want to be, all the questions then would be focused on that. Okay, and you'd be answering things about this. Just look at this data to try and figure out what we have is really important. And I didn't even answer the question yet. I didn't ask the question yet. All right, so here we go. All right, take a look at this guy. What do you think? Molecular formula has a molar mass of 2 straight chains listed here. And they're giving you a lot of information. Based on the information above, which compound has the higher boiling point? It's going to be this guy because of London dispersion forces. And you'll pick out which one we got here. Hydrogen bonding is out. Oh, here's that key term here. And that is what we want. Okay. You check the other ones out, but they're just going to be something in them that's not going to be correct. Dipole's out. This one's talking about London dispersion forces, but it's backwards. Because the molecules are smaller and they have closer together, resulting in stronger dispersion forces. No, that explanation is not correct. All right. All right, dipole. These are the same thing. Okay. These molecules have small but permanent dipoles. They are polar. They attract to other poles. Okay. There's a notes here that if they're this color, typically means that it's not in your book, so you can add this to your particular book. What is and what causes a dipole moment? Okay, so in this situation, you make sure you're aware of that anytime you have two atoms that do not have the same electronegativity, meaning they're not the same atom, then there's going to be a certain amount of electronegativity difference. So anytime you have an electronegativity difference, you're going to have a dipole moment. Okay? Larger the dipole moment, the more electronegativity difference, the larger your partial charges might be, and the more you're going to be able to attract to another one of these guys. Sometimes they refer to this as a dipole moment. Sometimes they refer to this as a dipole moment. Okay, so it's a difference of charge essentially. Um, what is and what causes dipole moment? Okay, so using the model above to the left, create a dipole moment in the model to the right. Label the charges, label the dipoles and partial charges. So all we're going to do, we got 6 electrons here, so I might just do this: 1, 2, 1, 2, 3, 4. Partial negative, partial positive. Okay, and of course I could do the same thing. Another one here, which would be positive 1, 2, 3, 4, positive 1, 2. Partial, negative, partial, positive. Now here, this right here is the dipole moment. Okay, so that's important. Next thing here, again, why would the electrons be moved over here? Because this guy likely has a higher electronegativity than this one does. Okay, so there's a difference of electronegativity. All right. What is a dipole What is a dipole and what's a dipole attraction? Okay, again, we just showed that all these terms kind of mix in with each other. There's a dipole moment here. Okay, creates a dipole. Dipole moments and dipoles. And dipoles attract. This is their partial positive, this is partial negative. Okay. Is hydrogen bonding a dipole-dipole attraction? And the answer is yes. It's a very specific form of it. So we have a hydrogen atom, okay, hooked to a highly electronegative atom. This highly electronegative atom will cause, therefore, partial negative, partial positive. It's a strong version. It's a very strong version, very prominent in biology. X typically would need to be nitrogen, oxygen, or fluorine. Okay, so example of HF would be hydrogen bonding. In the box below, draw a few HF molecules and exhibit hydrogen bonding. This is a really common problem here. So this would be like that. And then to show hydrogen bonding, you might do a dots, H, F, and then you might do like this. Do not draw it as a full dash. That would be a big no-no. Okay. This is a covalent bond, and this is the intermolecular force. Intermolecular force of hydrogen bonding. We don't typically abbreviate HB as hydrogen bonding on a test, so just short one right out. London dispersion forces, yeah, they'll abbreviate that one, but not hydrogen bonding. All right, move along here. All right, so how or why do electrons get dragged to one side of the molecule? Okay, and again, causing a dipole moment. What causes a dipole moment? Electrons being dragged to the other side of a molecule. So this would be a difference of electronegativity. Difference of electronegativity. How is electronegativity difference calculated? And now I'm going to show this example, but typically we wouldn't calculate on the fly like this. It's not something they're going to ask you to do. I'm not going to ask you to do it, but you got to understand it. Each atom has electronegativity. Each bond gets an electronegativity difference. Just simply take these guys and provide the data, and you subtract them. 3.0 minus 2.1. All right, you subtract out, that's 0.9. 0.9 falls in the range of polar covalent. So that means we're going to have charges. We're going to be polar. If the difference is so small that there is, in this range here, we would consider it basically to be nonpolar. Would there be some microscopic amount of dipole-dipole attractions in this guy, dipole attractions? It's not going to be a determining factor. Would there be some there? Yes. If they ask you to label all forces prominent that are here, you'd want to add it. Only way that you would nix this thing entirely is if you're literally at 0, which is coming up here in a moment. Okay? So, only way to be 0 would be to have the exact same values here, correct? And then you'd have 0. Only way to, again, if they ask you, it's there, but it's not something that is going to be causing a general effect. All right. Can you calculate dipole moment without math, with this math? The most common version is literally if it's 0. So N triple bonding to N like this. What's the dipole moment of this guy? 0. Why are they the same? Because they are the same atoms. Another example of this, I'll add in right here, very important, is symmetrical. Symmetrical. If an atom is symmetrical, then all charges cancel, and you're not going to your chances for a dipole are out, and therefore you have a dipole moment equaling 0. So two ways. Now some people, their pathway is a little bit different. Some people's pathway just starts with, do I have a dipole moment or don't I? If the answer is 0, dipole moment of 0, then you just run, the only thing you have is London dispersion forces. That's all you get. Okay? All right, some people's pathways start with this guy. Do I have a highly electronegative atom? Okay? Now again, this is not the only way to get a dipole moment. All you need is a difference of electronegativity to get a dipole moment. A significant dipole moment, you need one of these highly big guys. So anytime I see a molecule with one of these guys in it, right there, I'm thinking to myself, my brain starts dinging on the idea, oh, I might have a hydrogen bonding or a dipole-dipole attraction. Okay? So look for one of these guys. If I have one of these guys, then I don't need to do all this math. Okay? I'm more looking at this idea. Is it 0 or is it significant? Okay? And then I move from there. All right, so dipole moment. Larger difference of charge equals larger dipole moment. Larger dipole moment equals more Coulombic attraction. Is it possible to have a dipole moment and not be polar? And the answer is yes. All right, okay. Just in this case, you can have a dipole moment and it can be small. Okay. Lots of times you might see something like this, carbon dioxide. It looks like that. It's symmetrical. So some might say, you have is there a dipole moment here? Well, you have a polar bond here, but because you're symmetrical, your dipole moment is 0. So there's a few ways you could word this. Essentially, you know, something to think about. Okay, understand the concepts. They'll apply them to data provided. Look at here. There are two ways for M to have a dipole moment of 0. All right. So one is going to be, we already reviewed this, would be to have the same atom. Okay. Same exact electronegativity, 0, or to be symmetrical. Okay. Can a molecule have a dipole moment and still be nonpolar? Okay. You have a 0 dipole moment or a minimal dipole moment. Okay, so still would be nonpolar with minimum. Okay. So just some thoughts processes here, something to think about. All right, so symmetry. So I'm just going to briefly talk about symmetry and then this video is over with. So because symmetry can cause you have a dipole moment of 0, then symmetry is really important here. Okay. Here's kind of the general rule of thumb. Every single atom, the central atom, determines your symmetry. Every single atom has what we call um, electron domains around an atom. Okay. There are only a couple different types of electron domains. There's a handful of them. And I'm not going to show them right. I guess I'm not going to show them here, but essentially your central atom has things going off of them. 2 things, 3 things, 4 things, okay? Every single shape always starts out symmetrical, all right? So because they're just repelling away from each other and they're just forming a balanced position. No matter what you have, it always forms a balanced position. So how can it be that this isn't balanced? Well, in this situation, if we have bonded versions versus unbonded versions, that is where we start having things become asymmetrical. So a rule of thumb here is that if you have unbonded pairs on your central atom, then you are not going to be, you start out, if you have something on each one, you're going to be symmetrical. But if those things are removed, then you become asymmetrical. So anytime you have unbonded pairs on the central atom, you could say with a certain amount of truth, there are some exceptions, this thing would be asymmetrical. Now again, we have all oxygens here. So the dipole moment is 0. So it doesn't even matter, but it is asymmetrical. Okay, this has a dipole moment of 0, all at same electroactivities. Water, for example, again, here, I put hydrogen here. Then you have water, and once again, this is asymmetrical. Okay, so just general rule of thumb here. Okay, we're going to look closely at these structures, but look at this guy. Carbon, you could draw out the Lewis structure, all right, and 4 things off a center, all the same atom, that's symmetrical. This guy here, okay, oxygen, oxygen, a double bond there, and we have that guy. Is it symmetrical? No, asymmetrical. Why? Because that guy there, if it had 3 things off the center, it would be symmetrical. But it doesn't. It only has 2. This one's empty, so it's asymmetrical. Sulfur dioxide. I believe that one looks like this. All right, is it symmetrical? And this is yes. Okay. Moving along as quickly as we can here. End presentation. Thank you.